Okay, so what we're really seeing is if the values of f of x comma y approach L1 along one path to the point AB, while the values of f of x comma y approach another number, let's call it L sub 2, along a different path to the point A comma B. And if L1 and L2, yeah, I already said, I guess, another number, but here it is in the notation. If L1 is not equal to L2, then the limit of the function as xy approaches AB does not exist. So it'd be nice to figure out if a function given by formula, such as this one we saw just a moment ago, um, if that does not have a limit as xy approaches AB without having to draw the graph, which is three-dimensional, or even for that matter, having to draw the contour plot, which is many two-dimensional pictures. Mainly because both of those drawings are time consuming. So is there a way to do this that does some algebra? And let's just note that for the last example we looked at, the function, I guess we called it g of x comma y earlier, but its formula was x squared minus y squared over x squared plus y squared. We had seen that the contour plot showed different straight line paths to the origin having different z value. And so could we do something with that? Right? There were lines of different slope going through the origin having different output. And it was what I mean by that is one along all the points on one specific line of a certain slope had the same z value, and then if you look at a line of different slope, all those points had the same z value, but the z value then was different from the previous. So let's try to figure out how to do that same thing without having to draw the picture, right? So what we want to do is, for instance, see what happens to the z value for all the points satisfying y equals 4x, for example, and then see what happens to the z value for all the points where y is equal to 3x, which would be a different line through the origin, right? So we'd like to try to travel along different lines through the origin to lead up to the origin and see what happens with the z value without drawing the picture. Can we do this algebraically? So, given the function f of x comma y equals x squared minus y squared over x squared plus y squared, let's prove that the limit of this function as xy approaches the origin does not exist. So what are the values of f of x comma y along the x-axis? So in other words, when y is equal to 0. Well, we'd kind of already talked our way through that a little bit, but let's just write this out. Let's do a little bit of algebra before we do some calculus here. Just replace all the y's with a 0, and you have x squared over x squared, which simplifies to 1 as long as x is not equal to 0. And the point is that the values of f of x comma y approach 1. In fact, it's 1 the whole way there along the two x-axis paths. So if you start from the positive x-axis and just head straight to the left towards the origin, you'd get 1. And if you started on the negative x-axis and head straight to the right to get toward the origin, all along that path, the z coordinate is 1, right up until you get the origin where the function is undefined. Right? So there are those two paths. What about the values of f of x comma y along the y-axis? So when x is equal to 0, well, let's plug in 0. That should be so f of 0 comma y. Sorry for the typo there. This should be 0 squared minus y squared over 0 squared plus y squared, or negative y squared over y squared. As long as y is not 0, this is going to simplify to negative 1. So values of f of x comma y approach negative 1 traveling along the two paths, whether from above or below, and then headed towards the origin. The z coordinate is always going to be negative 1. Therefore, the limit doesn't exist. Let's try another one. So how about now the function is f of x comma y equals 2xy over x squared plus y squared. I'd like to look at the limit of this function as xy approaches the origin. Like the previous example, let's try traveling along lines through the origin with different slopes. So in fact, what we're trying to do is fix an m for a moment and then talk about the line y equals mx and see what happens, and then maybe change to a different m and see what happens. But let's not plug in for m. Well, I guess we'll do it this way this time. Let's travel along the line y equals 3x, meaning replace every y with a 3x, right? So after the comma up in the question was a y, now after the comma, it's 3x. So f of x comma 3x. And so replace every y with a 3x and work out some algebra here. Skip some details, right? The denominator should be x squared plus 9x squared, so 10x squared in the denominator. After cancellation, which is valid as long as x isn't 0, then you'll get the number 6/10. But then if you travel along the line y equals 4x, you're going to have x 8x squared over 17x squared, and you can cancel as long as you're not right at the origin, and you'll have the z value being 8/17. So look, the limit along two different lines is different. So all along one line, the line y equals 3x, the z value is 6/10, and all along a different line, the z value is 8/17. Now we could have compacted this work. This is what I was trying to talk about. We could have compacted this work by plugging in for m later. In other words, traveling along the line y equals mx without, I mean, let's not think of m so much as a variable. Think of it as a fixed number that we just don't know yet. Then you'd get something that looks like this. Factor out that x squared in the denominator, cancel the x squared on top and bottom, which is valid as long as x is not 0. And you have 2m over 1 plus m squared, right? And that number is 6/10. That number is 8/17, depending on what m is, for instance. And so the point is, you can quickly see that the z value, just to pick a new m, to pick a new slope here, the z value is 10 over 26 when traveling along the line y equals 5x, and the z value is 12 over 37 when traveling along the line y equals 6x. So just maybe it's a slightly quicker argument. I mean, it's, I guess, a little matter of personal taste. Let's take a look at this one. The limit of the function 2x squared y over x to the fourth plus y squared as x comma y approaches 0 comma 0. The idea again would be to travel along lines, right? To look at y equals mx. So we'll plug in mx for the y, and so f of x comma mx looks like this. And if we work out, let's see, x squared times x in the numerator, x cubed, yeah, 2mx cubed. In the denominator, you would, rewrite mx quantity squared. I don't need to go through all this algebra, right? Factor out an x squared, and you'll notice, I guess an x squared will cancel on top and bottom, which you could write out the work for. It looks like this. Just sorry for being very limit happy in the notation here, but you end up with the limit x y approaching 0 0 of 10x over x squared plus 25. And the point is that this is going to equal 0 because as you approach the origin, you don't have a denominator of 0 anymore with this plus 25. That's saving things nicely for us. And therefore, this ends up being continuous at the origin is really the wording. And so we can just plug in 0 for x. If you travel along y equals 6x, you have essentially the same issue. Sorry for the typo. This should be a 12x here. And you'll still get a 0 here. So the thing is, you're going to get the same limit whether you travel along the line y equals 7x or y equals 8x and so on and so forth. The problem is there's this extra x in the numerator. And right here, and so what caused that? What reflected that back in the original function? The limit always becomes 0 traveling along lines. So is the limit actually 0? Well, not so fast. Let's actually travel along the parabola y equals k times x squared for different values of k. So back to the same question, traveling along a parabola this time is going to work in kind of strange ways for us. So notice when you replace y with kx squared, the key thing to note in the denominator is you're going to have the power of x in all the terms finally be the same. We didn't have that earlier. So then factor out an x to the fourth in the denominator. Now an x to the fourth can cancel on top and bottom as long as x isn't 0. So you have 2k over 1 plus k squared. Now I think we see that there's going to be a problem. Yeah, this fraction, 2k over 1 plus k squared, is going to give us different numbers for different values of k. So these different parabolas that go through the origin will lead to different limits, right? So travel along the parabola y equals 3k squared, and the z value is always 2 times 3 over 1 plus 3 squared. Travel along a different parabola, the z value is 10 over 26. right? So therefore, the limit doesn't exist. This is tricky to do, right? This is not easy to build that intuition, I guess, to say, how do you know? Should you travel along lines or parabolas? But you've got to really look at the function you have and look at the relative degrees of things and go, aha, an x to the fourth plus y to the second, only to the second, huh? And use that to try to figure out should you travel along lines or parabolas and that kind of thing. This is by no means an easy task, and you might even recall that in Calc 1, strictly speaking, limits are not very easy to do, right? So you might not need to travel along paths that are lines, right? You might need to travel along other paths, look at the formula for your functions. Your goal is to try to figure out a way to get all of the x's to cancel by choosing the right thing for y, right? So y equals something involving x.